everybody. I have one that's going to be pretty quick. It's a result that deals with non-negative real numbers. We're supposed to show that a squared plus b squared plus c squared is greater than or equal to the product of all possible products. These are like the symmetric polynomials in two variables. But in any event, as long as a, b, and c are non-negative, this is not too hard to show by just using the arithmetic mean result 3 times. Now, just an example of, this is not too hard to prove, but let's just work with a concrete example. What if we had, let's say, 6 plus 4 over 2? That's real hard, isn't it? Okay. Well, that's certainly equal to 5. But notice that this arithmetic mean, geometric mean result shows that this would be strictly greater than. It says greater than or equal to, but we can put strictly here because we can see that it is. That's a 24, folks. That's the, okay, that's 24. And of course, 24 is 6 times 4, and this is equal to 5 over here. Okay, so it's not too surprising, this result, I guess. It follows pretty, the proof of it's fairly straightforward. But here we do have a strict inequality. So this is if it were 5 plus 5, that would be 5 plus 5 over 2 is 5, and then 5 times 5 square root is 5. So it would be equal if the 2 input arguments are the same. But anyway, we'll take this result to be true, and also you can manipulate it from the beginning because these same manipulations would occur when you're actually proving this result down here. But if you multiply through by 2 and square, you get this expression. And note that a plus b squared actually is a squared plus 2ab plus b squared, right? So you can see why this part over here, the right-hand side, has to be true. That 2ab would subtract off from this 2ab, and this is kind of the working result that we'll be using. Okay. We do know that a squared plus b squared is strictly greater than 2ab. And you can see that we just used that 3 consecutive times. Okay, we use that 3 consecutive times here, here, and here. And then properties of inequalities indicate that we can add these inequalities. But notice that a squared happens twice, b squared happens twice, and c squared happens twice. All right. And of course, there's 2's on the right-hand side of the inequality. So what we get right here is this statement here. And then dividing through by the positive value 2, we actually get the final result. Okay. I'm sure there's a way to do this using the Cauchy-Schwarz. Anyway, I hope that helped. Let me know.